Today I'm going to go over these tutorials here. I'm actually gonna go over the code, and then if I don't understand something, then I'm gonna probably read the tutorials with the text-to-speech. But I'm gonna talk about some stuff that I've learned. I read pretty much the tutorials up until a point, and I read back these Scratch Pixel tutorials. I think it's getting more clear in my mind how everything works. But and there's a bunch of the other thing that I realized is that I should look for implementation of 3JS using C++, because why start from scratch if someone else might have done it already? And then I found this one, so that's probably another thing that I'm gonna do. So I think maybe it depends on how much time I spend on each thing, but after I go over some of the examples here, I'm also gonna go over the 3JS code because I also spent some time looking at the 3JS code, and I'm trying to merge the two so I can translate the 3JS version of the stuff that I had into OpenGL. And the reason why I decided to study OpenGL is because I was trying to do it with Raylib, and then Raylib uses OpenGL, and I realized that I don't like I already studied this in the past, but then I forgot how the specifics and the nuances of how things work, and it's still kind of blurry to me, so I'm gonna try to make it more and more clear so I can do everything pretty much. So let me put some music. I think I'm gonna go over the stuff that I have here first. The notes that I took. I think those are, let's see the mouse. Those are just stuff that I wrote for Raylib that I'm probably gonna go over. Is the main structs that they use. So the mesh uses the shader created by WebGL renderer class. The geometry is just a class that manages the data used in order to change the variables, uniforms, attributes. I think this one I'm gonna talk about once I go over the 3JS code. So the coordinates is the thing that is most confusing to me because there's a bunch of different coordinates and it's very confusing to think about. So the way that it works, these first notes here that I took was from the Scratch Pixel. And there's a lot of information here. A lot of this information is not relevant to me. So if you don't know anything and you want to draw something from the beginning, then if you don't know mathematics, I suggest you start with these ones from math, but don't look into the Monte Carlo ones because they're not very relevant. So I would read these topics here first if you don't know mathematics. And then the one that is the most useful, I think, is this one. But probably the other ones, I don't remember the other ones very well. But the article that they talk about the coordinates is this one. So I went back to this article and I read everything. And it's making more sense to me now. And then this tutorials here is the OpenGL tutorials that I'm going to look into the code now. And they also talk about this text here. I think it's not this one, is the coordinate system one. They also explain the relationship between the coordinates, but the thing that is kind of confusing is that here they use two different names. They use screen space for saying two different things. So here, when they say screen space, they mean one thing, and on the Scratch Pixel, they mean another thing. But it's pretty much this pipeline here. So you have the world space, which is the space that has all the objects. Then you have the camera space, which is a local space. So the local space is relative to the world space. It's the same thing as in reality. Imagine like you have a camera and you are in a room. The coordinates of the camera is the camera space, and the world space would be the coordinates of the room, and they are relative to each other. Then you have the screen space, which is translating the camera coordinates, which are in 3 dimensions. So there's 2 different rules that they use to describe the coordinates. One is the right-hand rule, which is OpenGL uses, which pretty much means that the direction of the z coordinate is going to be positive for the inside, and then negative going in the camera or the visualization. And yeah, so pretty much like the weight of the hand. That you just do this, and then the X is the thumb, the Y is I think it is index finger, and the Z is the middle finger. It goes this direction, and then the other one is using the left-hand side, which is pretty much just changes the direction of the Z. So OpenGL uses the right-hand side rule, which means that the Z direction is going to be positive when it goes towards the camera, and not in negative when it goes towards the visualization. As far as I understand now. So what happens on from the camera space to the screen space is that it translates the 3D coordinates into 2D coordinates, because obviously the pixel is going to be 2 dimensions. So the way you do that, or the way that they say that this happens, is just by dividing the x and y coordinates by z, by the z coordinates, and that makes it so that you get the perspective of 3D. And there's some other nuances, but it's pretty much the main thing. Then from screen space, you have normalized device coordinates, and those coordinates are from -1 to 1, and they are the coordinates of the shader. And it's also called clip space, I think. So anything that is not inside of these coordinates gets clipped out of the visualization, and is like, as far as I understand now, is kind of like a standard that they created so that you can have like always the same coordinates regardless of what other stuff you're using, like the GPU and the pixel ratio, the monitor, all this other stuff, I think. Then from this coordinate, you convert to the actual pixel coordinate, which is the raster space. So this would be the pixels of the window you're visualizing. And this is pretty much just using a floor function, I think, which is a function that rounds the values to integers, because obviously the pixel is not going to be a float value, the actual pixel on the screen. So it's all integers, so it converts from the normalized device coordinates to the raster space, and that's pretty much it, I think. But I think that OpenGL tutorials, they call the raster space screen space, so that was kind of confusing. I'm not 100% sure, but I think because it's pretty much the same thing. They don't talk about the screen space here, they talk about it here, so I assume that they're saying the same thing but with different names. That's why it's kind of confusing. Convert from world space. So to convert from the world to camera, you just multiply, I think. Yeah, you multiply one matrix by the other, by point or world coordinates by the. And if you want to go the other way from the local to the world, then you inverse the local matrix, which is the camera matrix, and then you multiply, and you get the other coordinates. It's pretty much changing reference frames from where you are visualizing. And then the names here, which I remembered, but now is more clear what is happening. The model is the local. Model matrix is the local matrix, which represents the world from the point of view of the camera, for example, or any object. The view is from the camera, the model is from the objects, I think. But it's pretty much the same thing, it's just different relative coordinates, I think. So like the difference would be that I'm not 100% sure about this, but I think that the main difference is that the camera is going to have multiple different models, because the model is each object you have, and then the camera is the coordinates that are responsible for visualizing or creating the visualization of the objects. So I think that but I'm not 100% sure, because I think it might depend on the way that you structure things. So like there's a way that they talk about on one of the WebGL tutorials, which is just creating a tree hierarchy for a scene, which pretty much just means that you create order of dependence. So you can connect one model with the other one, and then if you do that, it changes, like once you change the base model, let's say, it changes all the other ones because they're like connected, they are dependent on each other. So imagine that this is kind of the logic here, where each model is connected with the camera, so the camera will be the parent one, and then the models are each object on the scene. So every time that something changes, it changes everything, because they're just multiplying one matrix with the other. The projection is the normalized device coordinates from camera to normalized device coordinate space. So in order to get the position, I think that you just multiply the tree matrix, and then the name is model view projection that people call it. But the thing that I'm not 100% sure yet is like what is the best way to do this, because some of the tutorials they do this calculation inside of the shader. Then on other tutorials, they just do it, they just pass the coordinates outside. So I imagine that the best way to do, the way that is actually done in practice is that you do it inside of the shader because you want to pass the coordinates from the program you're creating, the data. The coordinates are going to be the data that you pass through the shader to draw this stuff. So I imagine that the way that people usually do it is they pass the normal coordinates, the coordinates from world space or a camera space, which are not normalized. And then inside of the shader, they do the calculation to normalize the coordinates, which is just doing like a matrix multiplication inside of the shader, where you multiply these three different matrices, and then based on the data you pass, it's gonna update the position of the shader, the vertex shader, and then draw whatever the thing is supposed to be based on the data. But this is the kind of stuff that I'm gonna see now, I think. And it's gonna take a lot of time, probably. So maybe I should go over the pipeline that they explain here. I'm not really sure if it's on this one or the previous one or other tutorials. I think I changed the tutorial. So it's pretty much this, the pipeline. So we have the vertex shader, which is just data that you put points. So is this pretty much this here? This would be the data, and it's just an array of vertices. Then you pass this into a buffer, which you create with these functions here from OpenGL. And then, like based on whatever you pass here and whatever code you have inside of the shader, is gonna determine at which position you should draw the triangle that you're passing, or whatever other data you're passing. So from this, it goes to, it does this geometry shader, which I haven't seen too much, but I think usually use a default one. Then there's this rasterization, which is an algorithm that's gonna calculate, I forgot the nuances of it, but there's two different options. Either it's going to use rasterization. I think OpenGL uses rasterization, but another technique is ray tracing. And I think that's all that is doing is just calculating the positions of each pixel. So there is like, because the data is on triangles and the pixels are squares, and you can have collision between different triangles. I think the rasterization algorithm, what it does is just goes over each pixel and each triangle and then does some calculation to see if there are triangles that are overlapping, and if they are overlapping, which one is in front of the other one. And then based on that, it decides the color that the pixel is going to have. Not the color is the fragment shader. But yeah, I don't know the nuances very well, so I have to go back and study again. But it's something along those lines. And there's some articles here that talk about this as well. I think these ones. So I'm gonna have. Honestly, it doesn't matter that much to me now, because I'm more concerned about understanding how to structure the data and then how to think about the coordinates, so I can have a mental model in my mind of how should I draw stuff, how should I organize the classes to set up the data so I can pass to OpenGL functions. And then the rasterization is going to be handled by OpenGL, so it doesn't matter that much. Obviously, it's better to understand, but there's so much other stuff to understand. I already read this stuff. Oh, it's based on the barycentric, I think. So barycentric is a point like in the middle of the triangle. It's a good way to think about it. So it uses that to do some calculations over which one is going to be in front of the other, I think. But this one, as far as I've seen from videos and from articles, it seems that it's not the best one. The best one is ray tracing that everyone is using now, I think. And Vulkan uses the ray tracing. So it seems like ray tracing is better. The way ray tracing works, I understand a little bit more on the concepts, not the actual algorithm. But you're pretty much calculating, you're shooting the shooting rays based on the camera to see if they hit something or not. But this thing about shooting is kind of the confusing part that I don't like. That like all of the people describe it like this, but it's kind of hard to understand what this shooting mean. So as far as I understand right now, what it means is just that you're grabbing the coordinates of the... I'm not 100% sure which one it is, if it's normalized device coordinates or world coordinates, but you can imagine that you're just getting the coordinates from the world, and then you're creating a vector, which is just a calculation that is going to subtract the endpoint with the beginning point, and then based on the vector, you're going to see, and based on the other coordinates of everything that is happening on the scene, you're going to see whether or not the ray hits something. So the way that you shoot the ray is going to depend on the angle that you have from the camera, I think. And that's going to be part of the vector calculation. And then it's just going to be a bunch of calculations to see if the rays, different rays are hitting objects or not. And then based on whether or not they are hitting objects, you're going to determine if they are drawn or not and how much light they will have. So it's pretty much just rendering the things based on those calculations. The nuances of the calculations I don't remember really well. So let me go back. There's a lot of stuff to talk about. So based on this, the last step is the fragment shader. Fragment shader is just gonna color everything, and it colors based on the screen space, which is the raster space on the stretch pixel, which is the final space. Which is the actual pixels. So as far as I understand now, the fragment shader works based on the screen space. This is the final space that has the pixel coordinates. And then it's just going to color based on whatever code you put inside of the shader itself. So the way that it works with OpenGL is that you use buffers, and buffers is just a way to allocate memory on the GPU. So you can imagine that you're just selecting a space inside of the GPU of memory that you want to use, and then you have to specify how much of the memory you want to take and other things like that. So here, for example, it would be the size of the vertices, which is the data you're passing, and then you have to pass the vertices, which is the actual data. So you tell it basically tell it, I want you to separate these amounts, and this is the kind of data that I'm going to send you. And then based on that, it's going to understand that how to manage that data to actually do the calculations and draw this stuff on the screen. But it's very hard to understand in the beginning, because the hard part is understanding how everything is connected with everything else. So another thing is that you have this in and outs, and what this means is that you can send data from the vertex shader to the fragment shader, because the vertex shader runs first. So you can declare a variable inside of the shader code of the vertex shader that is going to be used on the fragment shader, which makes sense because after you know the positions that you're going to draw, which is the vertex shader, then it makes sense to let the fragment shader know about the data, so about those positions, so that it knows where to draw things. And that's pretty much how it's used as far as I understand now. And this location here, the locations from the vertex shader is just related to the buffer. So because of the way that the GPU draws stuff and OpenGL draws things, that it separates everything into the buffer, then you have to specify at what position each thing is, because everything is in bytes as far as OpenGL knows. So in order to know where to get the variable, you do this location to know which bytes are, what points in the buffer the information is at. So it's pretty much this thing here. So I have the position and then the size of the thing, which is just 3 things, and then it's like 3 variables that are floats. That's going to be the vector. and then you're telling how many of these should separate. And then there's different nuances as well on what kind of buffer you can create. So there's 3 different ones here. There's the vertex buffer objects, vertex array objects, and element buffer objects. And I don't understand very well the nuances of them yet, but all 3 of them, I think that they are used is the same logic. It's just buffers that are going to receive data, and then based on that data that they receive, they're going to run the shader code to draw the things. So I think that the main difference between the vertex buffer object and vertex array object is that this one is used when you want to reuse things, I think. Don't know very well. I don't know there's a difference between these variables here. There's 3 different variables, and they specify the gel static draw. They specify how frequently the data is going to change. Somewhere along here, I don't remember really well. But from another WebGL tutorial, I remember that if you want to draw more complex things, then you have to create a bunch of objects, and then you create an array of objects, and then based on that, you send that data, and then it's going to know. Or there's some code to draw a bunch of different stuff. Because this is the main thing that I kind of don't know how to go about it, because imagine you have a very complex geometry here, then obviously the way you're gonna do it is not by doing like this. You can use other software and other things to create the actual data, which is just the points that are gonna create the geometry you want. And then you also have the way that 3JS does it, and I think that most people do it, is to create classes that are gonna contain, for example, from the fragment shader, they're gonna contain the material and other attributes that the color of the thing that you want to draw has. And then that's the data that is going to be sent to the buffers and used as variables inside of the fragment shader to draw this stuff. So it's just creating a standard, which is a class that is going to contain the information that is used to construct whatever object you want. And it's the same thing for the vertices. Maybe I should go over 3JS first to explain this stuff, like, because if I go over the code, it's going to be easier to understand how 3JS does it. It's slightly different because WebGL uses left-hand side rule, which just changes the z coordinates, and OpenGL uses right-hand side. But I think that the logic is pretty much the same or very similar. So I did one of the examples manually here. And then I realized that you can just click here and grab the codes. And then also I'm going to go over their CMake code because I want to study the way that they did it. So you can just click here and then click the link and download the repository. And if you're using Windows, then my code broke. I download the code, then I built, then I put on this folder here. And if I try to run from the terminal, it breaks because it doesn't have permission to open the files. So any of the exercises that uses the shader, it doesn't work. So you have to run from the folder with permissions. So if you run like this, run as an administrator, then it works. But if you try to run from the terminal, it just breaks. At least it was working before. Maybe it's not working. Oh, it is working. Just taking more time, but yeah. So the way that I did it on the CMake is just to add subdirectory. So the main libraries that they use is the GLM and GLFW. This one creates the window, and this one is for math calculation, so for creating matrices and stuff like that. And then they use another one, which is STB image, which is a header file, and then it's just a normal, like a simple header file that you can get from one of the repos that they share on one of the tutorials. So pretty much just use add subdirectory, and this was working. And the way that you have to do it with the, I'm not really sure if it's GOM. I think the name of the thing is GLAD, so like they explain on the documentation you have an option to download the header version, and that's what I did. And if you download the header version, you have to put this define here, and this has to be before this include here. So yeah, so I think I'm gonna go over this code here, and then I'll go over the. This is the simple one that I did manually, and then I'm gonna go over the project here with the other examples. So the relationship between the camera, the main thing that I want to understand now is the relationship between the camera and the shader code, because I want to understand how I'm supposed to, what kind of data format should I send to the shader, and if the conversion between the world or local coordinates is going to be automatically done by OpenGL to get the normalized BIOS coordinates inside of the shader. So based on the whole pipeline there. And how is that going to relate to the camera? So this is the thing that is kind of the most confusing to me so far. So as far as I understand, like the way that it works is that I'm not 100% sure about the world coordinates in the beginning, but I believe that what makes most sense is just going to be 0, 0, 0, like the once you initialize the world, the string. And then the camera coordinates, you're going to create another class which is going to contain the information, which you're going to manually do the calculation if you're not using any library to handle the changes on the camera in relationship to the visualization, which is the world coordinates. So the camera is just going to contain, it's just going to be a matrix that is going to contain some positions, and then you use this whatever the name of this is, which is just a bunch of calculations on vectors to get the position of the camera, I think, in the beginning. I saw this one on Scratch Pixel, but I forgot exactly the nuances of it. But it's pretty much a bunch of calculations. So it's based on the up and the right vectors on the starting of the camera. I think it's on the look at function. I forgot which one was the look at. I think it's this one probably. Maybe it's on the perspective projection. Because this was also a confusing part for me. Is that the beginning when you initialize the camera, what's the relationship between the camera and the world coordinates in the beginning? And there is some part here that they talk about where it creates two different vectors, and then from those two different vectors, you do some multiplication or some math, and then you get the other coordinates from that. But I forgot which article it was. Was one of these? I think it was before this 3D here, because this is just the code for the conversions, and it's a simplified version, if I remember correctly. The way that they actually do is just by doing all the calculations at the same time, I think. But it's just like optimizations, and this shows the conversion between the different coordinate systems. I'm trying to find the one that's has the... Not sure if this one. Maybe it's this one. This is the thing that I kind of didn't like about this. I think the order should be the other way for someone that's starting. So you should read this one probably after you read the other ones about the coordinates here. So you should read these ones first, I think. Then you read the look at, because I think it makes more sense. But obviously, whatever, it's very good. All the articles are very good, I think. This is the calculations that I was talking about. So I guess it's the lookat function that does the... And the name of this calculations here is this name here. Gram-Schmidt process. Constructing an orthonormal basis from a set of vectors in a linear product space. Most commonly the Euclidean space. Yeah, so I guess like obviously you're gonna determine what is the initial coordinates of the camera depending on what class you're using or whatever you use to build the camera. But in the initial stage, there's gonna be these directions in the camera. There's just gonna be values. I think that it is a vector pretty much because it is the coordinates of where the camera is at, and also there's the frustum, which is gonna be the projection. So. Which is the angle that determines like how you're gonna see things. It's just two different. Maybe you can find another one that has the. I think the perspective projection. Because I don't know how to say that in English. The name of the shape that builds the thing. And this explains very well as well. So based on this, I think that what makes more sense is that the vertex data is going to be just the road coordinates, and then somewhere along the way, I think OpenGL converts them to normalize the base coordinate. But maybe you have to do that on the shader. I'm not really sure. You have to do the calculations yourself, and then you pass the matrices that you're using to create the road and the camera to the shader, and then based on that, you have to do the calculation, which is just multiplying the matrices so that the coordinates are right. And the shaders have this default variables. This is going to be the position of whatever you pass. So like the variables you assign are the ones that are going to receive the data, and then you can do the calculations based on the variables you declare here. And then from the outside, you're going to pass the data through the buffers using the GL functions. So this, where's the floats? Yeah, these calculations here. So we're going to pass the data, use the GL to functions to pass the data to the buffers. Then based on whatever you coded inside of the shader, it's gonna do whatever you tell it to do. Whatever you put on the shader is gonna happen. And then the variable that is gonna be used is the GL position to determine where the thing is gonna be drawn, I think. But it is not very clear to me. Like on the concept level, obviously, but on the nuances, it's still kind of confusing because it's hard to visualize the data. I think I remember somewhere that I got some visualization like that, but maybe I save it here. And this is just the orientation of the matrices. And that's how you rotate. So the reason why it's rotating is because each one of them, either rows or column, depending on the standard that you choose or that framework chooses, is gonna just be the points from whatever you're visualizing. So when you multiply the point by a cosine or sine, it's just gonna do the rotation, because it's gonna change the value of the coordinates, obviously. So multiplying by cosine and sine on this, the thing that is kind of hard to remember is exactly where should you put these values here to do the transformation. But you take this matrix and then multiply by whatever the position, the coordinates of the matrix that represents what you have is. And then once you do that, you're just gonna rotate the thing. So this rotates by x, this rotates by y, this rotates by z. And then obviously if you want to do multiple rotations at the same time, you would just put the same, the numbers on the same matrix. But the problem with that is that the order of the rotation matters. And then you get into something called gimbal lock, which is hard to explain. So like you can just search for the keyword. It's just gimbal lock. Gimbal lock, like this. There's a bunch of videos here that I watched as well. Explains this one, it's very good. And then for that reason, people use this Quartinium, which is just a 4D matrix that uses complex numbers to do the calculation of the rotation, which is just more efficient to do than to use the angles here. And this is the Euler way of rotating. But if you use Quartiniums, it does everything at the same time, and you don't get into this gimbal lock thing here. That's Euler rotation, which is very interesting. Because I think that the complex plane is fundamentally connected with space-time. The way that I imagine in my mind is that the complex plane is the imaginary plane that goes in depth, like it's the plane of imagination. So space-time is always connected with imagination because, and based on these videos, I think that I'm not really sure if that makes sense or not, but that space-time is either space-time is a projection of complex plane or the complex plane is a projection of space-time. But I think they are entangled. Let's say I think it makes more sense for space-time to be a projection of the complex plane because it seems that the complex plane has higher potential, and the space-time has more order, and that creates a funnel. And then the boundary between the two creates reality. So that's the reason why I think that Quartiniums are more efficient to rotate the objects, because you're using like higher dimensional plane to do the calculations. But I don't know about the details very well. I'm not sure, man. Also, I found this channel here. I highly recommend. There's so much stuff to watch. It's crazy. I'm probably gonna watch the videos later. So let me go back. I think I was talking about the projection. I'm probably not gonna find the picture, but I think it's pretty much what's happening. So you initialize with the angle, which is gonna be the field of view, and then you have the other values, which is the z near, which is just the plane that is near the camera, and then you have the z far, which is the plane that is far, and just different coordinates that you put to represent the field of view that you're gonna create. Just different planes connected. One is gonna be bigger, it's gonna be further away. The other is going to be smaller and it's going to be closer away, and that's going to create the illusion of the 3D. That's why it's perspective projection, the name. And the calculation is going to be done. It's just going to divide the z coordinate, the x and y by the z coordinate, and that's going to make it so that the GPU draws in a way that gives the illusion of the 3D based on the angle and the data. So you can imagine that the beginning, you're going to have this numbers that represent the camera, whatever camera you're using. And then you're gonna have to relate the camera with the position of the object. And that's where it gets confusing, because that's where you're gonna have these translations here. So I believe that both the camera and the objects are gonna have local coordinates in the beginning. And the local coordinate of the object is gonna be the data that you send. But maybe it's the world space that you should put the coordinates as world space in the data you send. But this is the part that I kind of want to clarify, because here it seems that they put on normalized in the device coordinates space already. So maybe the way you organize here has to be normalized. But maybe I think that actually the reason why they did it like this is because they don't have to calculate, because this is a simple example. So because the simple example is using a simple shader, and the shader code probably doesn't translate the coordinates. So that's probably the reason why they send it like this, because then it's already on the normalized version. But I think in the way that most people do it, or the way that's going to happen in practice, is probably that you're going to pass the data in world coordinates, and then inside of the shader, you're going to have to do the calculation to transform the world coordinates into the raster space coordinates. And the way that you're going to do that is just by multiplying based on these matrices here. So usually, probably you're going to have to declare 3 different variables inside of the shader, and then you're going to have to pass, after you initialize the camera and you have these values of the field of view and all this other stuff, and the values of the world the value of the world matrix, then you're going to pass that data to the shader, and then it's going to use the shade that's it's going to multiply. You multiply the matrices to convert whatever is the coordinates of the data you're passing into normalized device coordinates. And that's going to make it so that you have the thing on the screen. So I think it's becoming more clear on my mind now on how it works. Let me... So this is what the code here produces. Just a normal. But I think I'm gonna go over the other ones now. And I want to look both into the C++ code and the shader code, obviously. But I'm gonna look into this one first. So maybe I should go over and explain. So this stuff here in the beginning is just using this GFLW library to create the... this I put here, but it's not related. I was just testing to see if the library was working, the other one. But this one pretty much just initializes the things for the window, to create the window. So it doesn't matter that much. And it's all setup codes. And yeah, here this starts creating the shader, and they recommend to use this GLAD library. I still don't understand very well. I want to understand. Probably gonna ask on the Raylib Discord if anyone knows, but it's kind of hard to know exactly how this interface works. So this library is pretty much an interface between this code here. So like the functions you're calling here are gonna be definitions of macros that are based on OpenGL functions. So it creates an interface between you and OpenGL. But I don't understand very well why. And I also don't understand very well how to get to understand how they work and why do you use this. Because you can use the OpenGL functions directly without using GLAD, but they recommend to use GLAD, so I'm not really sure. So it pretty much creates a bunch of pointers here that work as an API between you and OpenGL, but I don't understand why. So I want to see if anyone understands this later. But pretty much, so this is kind of a problem because I don't know, and I think I'm not really sure if you can know this or not. So like I'm going to study this later, but just based on the name, you can kind of tell what the function does. But obviously I don't know what is happening in the source code. So yeah, but it creates the program. It's just going to be an integer, then attaches the shader, both shaders, which are the codes here. They created in the beginning to that program, So obviously the program is going to be the thing that draws this stuff on the screen, and then it just links the two different shaders, the vertex shader and the fragment shader, to the final thing so that you can draw stuff. Yeah, so it just does this stuff. Then links the program. And you should call the GL use program inside of the loop of the drawing. The other functions is just setup functions that you call side. But to actually draw, you have to call the GL use program like inside of the drawing loop. Here declares the data. It's just a basic example, but you have to manually declare where you want the points to be, because because these coordinates here are 0, it means that the z is going to be 0. But then if you want to change, you can obviously put different data here. And then this VBO is the thing that I'm not 100% sure yet, like how the nuances of this works. But it's just creating objects, I think, inside of the buffer that are going to allow you to specify how the buffer is going to read the data to use the data inside of the shader to draw the stuff. So we just call these functions to set up the shader with these things here. It's kind of like works like flag variables. So this is the main buffer that I think they use here, this GL array buffer. So this is pretty much saying initialize this GL array buffer with this VBO object, which is gonna determine how you should use that array to use the data on inside of the shader. Then you call this function, which passes the data, which has the size of the vertex, the array that we created here, and then it specifies the data, and then it specifies how to use that data. Let me see if because they do talk about 3 different ways here. Yeah, this one. So the for parameter specifies how we want the graphics card to manage the given data. String draw, the data is sent only once and used by the GPU at most few times. The data is sent only once and used many times. The data is changed a lot and used many times. So I'm not 100% sure about this stuff. I'm gonna have to study a lot more to understand how exactly you're supposed to create each thing. But I'm also gonna go over the raylib library at some point, because I'm obviously using raylib, so I wanna understand how they set up everything. So based on the stuff that I did last time that I streamed, I already understand like they pretty much create functions to automate all this process in the beginning here. So think about it like creating a function where you put all this stuff here, and then you create a map or something like that or an array that is gonna map the index with the shader or with the buffers you create in the beginning. So they already have standards that represent the location of where each variable is going to be inside of the shader. And then they map those things with the program, which is going to be a struct that they use to manage everything. And the struct, I think, is the RGL data struct. So this one is going to hold, if I remember correctly, it's going to hold the shader, which is another struct that contains an array that maps the buffers and the locations of the variables of the shader that you're initializing. But I'm gonna go over like a lot more. First, I'm trying to focus on this like simple stuff to really understand the fundamentals of how exactly it works. Then once I feel like I grasp that very well, then I'm gonna go back to the raylib to try to also, I think before I go to raylib, I'm gonna study this one, and then I'm gonna try to incorporate this one, because this one doesn't use raylib, it just uses OpenGL and GLFW, I think. But I'm gonna try to get the code from this one, get the classes, and then modify these classes to work so that they work with raylib. Obviously, I need to understand more on how exactly the nuances of the thing works. The biggest thing that I'm trying to make it clear here, that is becoming more and more clear in my mind as well, is the relationship between the vertex, the shader code, and the data outside of the shader. Like, how should you think about those things based on the coordinates of each thing? That's the part that I think is most confusing. So I'm trying to clarify this connection. And it's like those things in relationship with the camera. So the world coordinates, the camera coordinates, and how they relate to the shaders you're gonna build to construct the visualization in the end. So here's the render loop, another function that just checks to see if the window is closed. Then this is some function that they create to process inputs like keyboard and mouse inputs. But I think they didn't do anything in the first examples that I saw. Here's almost the final. So another OpenGL or glad functions that just clear the color and then puts clear the buffer, the color buffer. Then this is the one that uses the program that was created here at some point. Yeah, this program. So I created the program, links the shaders, and the shader source code is this one's the fragment here, vertex here. Then like passes the data through the buffers. And then here it finally uses the shader, the program. Here I'm not 100% sure, but that is the other one that I have to study more to understand. The vertex array object. So it's binding that to here, and then finally it's calling this to draw the shape there. And I think this is another glad function, OpenGL function. It's gonna draw. And the reason why I can do this is because it already has all the data on the shaders. So I think I'm gonna go to the other examples. Maybe I should look into the shader code here. Here is just specifying one variable and saying that is on the location 0. So you can imagine what I think is happening is that you're gonna have that thing here, this thing. So the location is the bytes here, I think. So it separates everything based on these strides, which is going to be the size of the data you're passing to the buffer. And then the location is going to be whatever it is. It's kind of like arrays in C as well. Like if you create an array of integers, for example, each index of the array is going to have 4 bytes because integer is 4 bytes. So as far as I remember. So it's the same thing with the buffer. Like depending on what kind of data you pass, is just going to have the different strides. But then the location is going to be like the index of the array. So it starts on the 0, then obviously goes 1, 2. So I think that's what's happening there. Like when you declare this as location 0, you're just saying to that the variable, the data that is on the index 0 on the buffer is this variable here. So I think that's what's going on. So later on, when you pass the data, then it knows like how to make sense of that data, those bytes, inside of the shader program, or how to use the bytes you pass as data instead of here. And the bytes you pass are just the vertices here in this case. So yeah, that's why you have to determine like this is the size, which is going to be the stride here, size of the type of the data, and this is the data you're sending. So this is going to determine how many indexes I think the buffer is going to allocate for that size. So like you can imagine, I think like if you're passing more than one vertices, for example, like if you're passing another data structure that contains a bigger index or contains this one, like here, something like this, then it's just going to be the same thing, but like on this example, you can imagine that the only thing that it has is the vertex 1. And then if you put more data inside of the vertices, it's just going to split that data based on whatever size you pass here. It's the size of the bytes that is splitting the buffer. And then based on the location of the variables inside of the shader code, it's going to determine how it uses that data to do whatever calculation you want here. And then it uses the shoe. I think the main variables that I saw so far is the shoe, different ones, the GL position and the frag color. GL position is obviously where the position of the thing is going to be, where you actually, the position of the points, or the triangles you're drawing with the GPU. And then the frag color is what color the pixels are going to be, I think. So here is very simple. It's just declaring vector 3 position. Then the position is just going to be the vector 4 that has the whatever x, y, and z are. So I think that's, yeah, this is, no, I'm not really sure though. Because probably what's happening is that this is being called 3 times, obviously to draw the triangle. That's what makes the most sense to me. So if this is being called 3 times, then it means that it is splitting this data 3 times. But it's kind of confusing because I don't know now. Because the size of is from the whole thing, so. So I'm not really sure. I think that the explanation there, it makes sense. Like it is splitting, but I'm not sure about how much is splitting for each thing. So maybe I should read this stuff again. This is for the other example. The thing is, I don't think that they, oh, here. But they don't show with visualization on this one. The vertex buffer object currently bound to the GL array buffer target. Second argument specifies the size of the data in bytes we want to pass to the buffer. A simple size of the vertex data suffices, or suffices, whatever, however you say that. But the third parameter is the actual data we want to send. So I guess but the question is, how does it split the vertices? Because obviously it's drawing 3 different points, and based on the shader code, it means that the position is just the x and y, z from the points that it's passing. So I don't understand how does it know when to split each thing. I guess it might be based on the size of the variable you're passing. So I have to keep track on, but like this is one of the things that I didn't like about OpenGL, is that like as far as I can remember, I'm not 100% sure, but I think if you're gonna pass multiple different things, like if you wanna use multiple different buffers, it's not very like you have to remember which one you're using, because first you have to call the functions like this, and then you call the other functions like based on the same variable here. So like the GL array, it becomes kind of confusing to remember what each variable is bind to at any moment in time, because they depend on the way that you call the functions. So that's the thing that is kind of confusing. So I think it's pretty much the same thing here. Like you kind of have to know in your mind which variables you're going to use inside of the shader, and then think about that when you're structuring the data you're going to send. But usually probably it's going to be it's not going to be that difficult, because it's either going to be a matrix or a vector, so you're going to know the size by hand, but it's still kind of, because you have to do it in your mind, the math. And also the other thing that I don't know very well is the orientation here, but I think the orientation goes back to this thing here. It's just a standard, so the way that they do it is like this. The x-axis is this, and the y is this, the z is this. So these are just the way you select the points. Let me see. Parameter is the actual data we want to send. The fourth parameter specifies blah, blah, blah. The position data of the triangle does not change, is used a lot, and stays the same for every render call, so its usage type should best be, for instance, one would have a buffer with data that is likely to change frequently. And with such type of GL, dynamic draw ensures the graphics card will place the data in memory that allows for faster runs. I think this one is the one that is used most of the time, probably. Because usually, but I'm not 100% sure though. I think it makes more sense because usually in the visualization you're gonna change things. So I think every time you change something on the visualization, you have to change the data you're passing to the shader. Yeah. I don't think they talk about here these things about the relationship between the location and the data you're passing. So maybe I should go into the other examples. First parameter specifies location of the position of vertex attributes with layout 0. This sets the location of the vertex attribute to 0. And since we want to pass data to this vertex attribute, we're passing 0. I guess I probably, I don't know if I should read this now or read this off stream and just go over the other examples. Because the other thing that I want to see is the camera. Is that there's another tutorial that they talk about the camera, but I just want to like make sure that the intuition that I have is correct. So I think I'm gonna do that. I'm gonna read this stuff again off stream probably. Maybe this part here. There's one last thing we'd like to discuss when rendering vertices, and that is element buffer objects abbreviated to EBO. Element buffer objects work. Smash should give an example. Suppose we want to draw a rectangle instead of a triangle. Can draw a rectangle. Yeah, but I don't know if they're gonna talk about like how. No, it's this thing here. So I think he uses another. I remember seeing this from videos as well. Index buffers. I think he uses another buffer to keep track of how to split the data. So it's kind of like splitting an array, pretty much, but in a more complicated way, because the buffer is bytes. So one of them is gonna be the data you're gonna pass. The other one determines how you're gonna split that data. I think that's what's happening. And probably the order you declare things inside of the shader matters. So what you declare first is location 0, and then after is location 1. So, but I'm not 100% sure. So, but if that was the case, then I guess it's because of the size. So is the thing. So if you don't have the index buffer, then you're just gonna do the calculation based on whatever size the variable has. So because it passed the data that has 3 different rows, and the size of the first variable is vector 3, it just splits this data here into 3, and then for each one it calculates the vec4 based on the position that it has there, and then based on that it draws so it draws 1 point at a time, and then at the end you have the triangle. I think that's what's happening. So let me go over the example, the camera ones. After I go over the camera, I'm gonna go to 3GS to talk about what I learned as I was going through the code. Don't remember which one it is. It doesn't have by the name there. It's kind of hard to organize in my mind as well, like what is the best. Because now I have 3 different projects that I'm doing. So I think that it makes the most sense to finish the shader part first. So I create another, like I have the main project, no, the beginning project that I'm using to structure things in the beginning, where I have the graph boost graph, and the simple visualization using the raylib functions. Then I created another project to do the shaders now, and then I created this other one to study from OpenGL from scratch. So I think that what I'm thinking about doing is probably going to the other project again, the shader one, and then from the shader I should try to incorporate this or study this code here on 3JS, and then try to incorporate these classes on the shader one. Then once I have the structure of the classes and like the shaders, this is another part that's going to be very hard, which I'm going to talk about I think after I go over the example, which is just the code here from 3JS, because the shader code that they have is very complicated. And this is another thing that I'm debating. I'm not really sure if it's worth it to do my own thing from scratch and ignore their code, because I think that a huge part of the complexity that they have is just because they want to fit into many use cases. So I'm not really sure if it's worth it to try to do it, to do everything from scratch. But probably best is to use this one, try to use this project, and then once I have the classes and everything like that, and I can draw the shapes that I'm gonna need. I'm probably gonna try to draw the particular shapes that I need without using the graph. Then once I have that, then I know I can just call those functions based on the graph boost data structure. That's gonna create the shape, I think. Then after I do that, then I can focus on the physics, I think. And once I close the cycle, then I'm gonna create another project probably from scratch, just to like the official one, to have the simulation. Then that's just the beginning, and then I have to do like a bunch of other stuff. But I'm learning a lot, so. Also, it's one of the, yeah, these ones. Probably the coordinate systems ones as well. And those, it's both that and like connecting the shader with the data and understanding the coordinate system translation. It's the hardest things to grasp now for me. I'm gonna have to go over the raylib source code again to really understand, because here they're using GLM. And I assume that raylib is doing the same thing, but I want to understand the way that raylib actually does it. So everything the same here, just different data. And now they're passing this data for the texture. Texture is related to the fragment shader, so that's going to be the color of the thing that you're drawing. Then it's separating the indices. So I think the logic that I have, the intuition that I have makes sense. The indices, you're just creating a complicated array manually, probably, pretty much. So the data, like you have the freedom to pass any data you want, which is just going to be an array of floats. And then it's your responsibility to tell the buffers how to split the data, so you can use the variables instead of the shader to draw this stuff. I think that's how it works. And then these are pretty much like flag variables to determine how OpenGL is gonna create the buffers to use the data you're passing. So calls a bunch of functions to create the texture. Oh, this is another thing, is to draw pictures or to draw fonts. it becomes more complicated because there's this thing that I think is called sign distance field, which is just other calculations you have to do in order to translate the format of the picture into bytes. So you can use that data to draw the thing on the using the shaders. But I haven't looked into this very much. But I'm probably gonna have to do that once it gets time to draw the labels. And there's some stuff about fonts from different operational systems, so I'm gonna have to look into this. But I haven't done anything yet. I wanna focus on the other stuff first, obviously. Then just figure out everything. Then once I do that, then I can focus on the label. So here, I guess, is the part of the camera. So up until here. So I think on these lessons, probably they didn't create the separate class. So there is a lesson that they create a separate class to have all the functions that are going to manage the camera. But I guess here they're just doing manually to show like step by step how you build everything. But it's pretty much going to be these three matrices, which is the stuff that I explained in the beginning. The model is the matrix that contains the local coordinates that represent the camera, I think. No, actually the view is that. The model is the matrix that represents the objects from the point of view of the camera, I think. I'm gonna have to look into this again, but as far as I can tell, I can remember, that's what's going on. The model is the objects, then the view is the matrix that represents the coordinates of the camera itself, and the projection is the matrix that represents the field of view of the camera, I think. But I'm not 100% sure though. I have to go back to remember. And I think what this is doing is just rotating, doing some transformation on the matrices. Let me see the example. I think it's this one. Oh, it's gonna crash. I need to run as a administrator. I have to read again to remember these details. It's not very clear to me. So I guess the main things the main thing that I have to review is this thing about the camera, about these three different matrices and what exactly do they represent. Because obviously there's gonna be the Z near and Z far as well. So yeah, I'm not really sure. Maybe if I look into the shaders also is gonna clarify. But I think what is happening here is just passing so it's getting the variable that is related. So in the shader, they probably have the model, which is a matrix declared as a variable inside of the shader code. And then this is just accessing that variable, or is accessing the location of the variable. And then this function is passing the location of the variable with a new value. I think that's what this is doing. And this is getting the same thing for the camera. And the variable inside of the shader is probably dependent on these other variables here. So just determining how you're using the matrices that are creating the view of the visualization and passing that into the shader code so that the position is dependent on the calculations of the matrices that determine the location of the camera. So you can put whatever you're visualizing in front of the camera. I think that's what's happening. Yeah. It's like it's a model view projection, and then you're just multiplying the three different matrices and the position. So this is just doing the translation. So like this is the relative position of the point you're drawing. Then when you multiply this by the model and the view and the projection, you get I think you get the normalized device coordinates, but not 100% sure now. Because obviously, like you said, to go from the local to the world, you do the inverse. So since it's not doing the inverse, I think it's going from the world to the normalized device coordinates. That's what would make more sense to me. I guess we can find out based on the data. Yeah, I think that's what's happening. But I'm not really sure though. I have to see again. I should read the stuff again. I'm pretty sure that inside of the shader is normalized device coordinates. But it's just the thing that I'm confused about is the translation, because I think that's not very clear. I'm not really sure if it was clear or not. I have to read the tutorials again. But the translation from the data, from the coordinates of the data to the coordinates that are done on the shader, which is the GL position. How exactly, like I think what it's doing is just getting these different coordinate systems that represent, each one represents its respective thing. And then when you multiply them, you get the absolute thing, which is the absolute coordinate. But I'm not really sure, which I assume that is probably going to be on clip space, or clip space, or what's the name? Normalized device coordinate space. So I assume that this is what's going on. But I guess it depends on the way you're gonna use as well, because if you pass other numbers here, I guess this is the thing, is like, it's not a fixed thing, it depends on the way you use it. Because if you pass the different coordinates as data to here, then you would do a different calculation, I think, to get the position. So maybe another thing I can see, but here it doesn't. So I assume here they are formatting normalized device coordinates as well, the initial values. We're not really sure. Let me go back to the tutorial. I think we're gonna read this again. Because it wouldn't make sense though to... because the multiplication is gonna be the conversion. So the view is the result of the calculation because of the lookat function. So you get the values of the positions, the up, the front, and then from the up and the front you get the right, I think. And then that updates the view. This is the matrix that contains the, obviously, the directions for the camera. Here they are normalizing. Also, they are calling this function here. So this is the function that's gonna change this array, this matrix. So I think that now, but I'm still not 100% sure though. So the projection, I think the projection matrix is just gonna contain, like, this is the angle, which is the field of view, which is gonna be 45. In this case, it's arbitrary, but the field of view determines how wide is the length, let's say. That's going to create the illusion of projection. So I think the smaller the angle, the less 3D sense you're going to have, and the higher the angle, the more 3D-like it's going to become because of the projection that is happening. So 45 I think is usually the one that they recommend. Then I think that this values here, this one I'm not really sure, but I think that this shoe here represents the planes that is going to create the projection. So 0.1 is the plane near the camera, and 100 is the plane far away, and that creates the sense of the perspective. And here I'm not really sure what this is. Maybe I can just look up the, or just ask ChatGPT. Aspect ratio. Yeah, I thought about this, but this wasn't sure. So the thing is, like, it's kind of hard to visualize though. Like, what is the... Maybe if I'll just go to the definition.
Let me tell you why you're here. You're here because you...
Put something. So I want to understand what the matrix is going to look like though. Like based on these values. So the 0, 0 index is the aspects. So it seems like it is... Like this is the diagonal, I think. The values in the diagonal. I think that's the part that I'm most confused about. Because obviously, just... like some values... But obviously the way that the matrix is going to look like at the end is going to just be like a byproduct of how the calculations are going to be like, because based on the standard here, obviously, like, but I guess I still have to trying to see if I can formalize the question. Because obviously those values are going to be used to, are going to be one of these values here, the far, near, and the values that the function receives here, the angle. But I'm still confused on which of these values is going to be, because obviously this is going to be multiplied with the other ones. So I guess this is the part that's I was confused about, the transformation there from the camera look at. So that's the thing that I will have to review. Because I think that those values, the way that the shape of the matrix is going to be based on the way that this calculation works, the look at calculation, because that's going to determine where the values of the arguments here are going to be inside of the matrix, so that once they are multiplied by the other values, it gives the correct equation from x, y, and z to do the transformation, I think. But obviously the lookout is going to be from this one. But maybe they are related, because obviously they're going to be multiplied to give the visualization. Yeah, so I think that obviously, yeah, that makes sense in my mind. So, like, the numbers are going to be anywhere inside of this, it's kind of hard to explain, but the field of view, the near and the far values, they're going to be anywhere inside of this matrix, such that when they are multiplied by the view matrix, which is the camera matrix, the matrix that contains the camera coordinates, they give the illusion of the 3D. And then like the result is going to be all the formulas where you just divide the xy by z. And I think that there are some other nuances that I'm not really sure, that I have to go back and look and read again read the articles again to understand. Maybe I should ask, try to clarify the questions though. So I think that one of the questions that I have to reveal or should try to clarify is what exactly does the model matrix represents? And how is it related? Because I have the intuition, but I'm not 100% sure if it is correct or not. So I think based on what I wrote here, my intuition is correct. So the model is just the objects, then you translate this matrix translates from the local to the road, and then you translate from the road to the camera based on the view. So like the model is just saying like go from the coordinates of the object and translate those coordinates to the absolute coordinates of the road position. Then from the road, go to the camera coordinates, and then from the camera project based on this matrix. And the configuration of this matrix is going to be done in such a way that when it's multiplied by the view matrix, you get the normalized device coordinates. I think that's which are based on the equations there that they talk about on the articles. I think that's what makes sense. But now the question that I still have is because I think that's the reason why it's confusing, because they are all gonna be different values in the beginning here. So like the way you pass the data is in a different scale. The numbers are on a different scale than the numbers on the matrices here, because they're using other different coordinate systems. That's the part that is confusing. But then when you multiply all of them, you get the normalized device coordinates. And then from that, I think that's the OpenGL. No, from that there is a function I think on OpenGL that is set up in the beginning. I think is gel viewports, that the viewport function or functions related to viewport from OpenGL are going to be the ones that are responsible for taking from normalized device coordinates into the window coordinates, which is just the pixels of the screen. And that's the final part, I think. So I think that the biggest question is if there's a standard to pass vertex data. Because this is the part that is very confusing, because like especially when we're talking about things that are going to change in the visualization, because obviously the data you're passing is going to determine what the GPU draws based on the shader code, based on the whole thing that I described. And like how can you picture exactly all the points that are going to be responsible for creating the geometry before? Obviously, from the videos I've seen from other stuff, usually you create models on other software and then it creates the data for you, and then you just use that file, or you just spend a bunch of time in the beginning, like, or like use a library that has done this. I think 3JS has done this on their implementation, where they just spend a bunch of time and then figure out where the points have to be to create the geometry, like where the values on the matrix have to be. But then like it's still kind of confusing because the coordinates are gonna be different, obviously, because it depends on where you want the visualization to be. So even though like the place where you put the values is always going to be the same because they represent the geometry that the thing is going to create. So I think here, for example, is creating a cube or yeah, a rectangle based on the values here. So like the location is always going to be the same to create the geometry, but the value of the location is going to be different based on where you want the geometry to be in the visualization. And the question is like, what is the standard way to the scale of the values of the floats you have to pass to the shader? I think that the standard is probably going to be on normalized device coordinates, which is just from -1 to 1. You have to pass the data as. And then you have to do the conversion yourself, and the way that you do it is either on the shader or outside by multiplying by these other matrices here. I think that's what makes most sense to me, but I'm not 100% sure if that's how it works. And if you have to do it either inside or outside, then which one is usually the best? Or it's kind of the other way around though. Like you're converting everything to the normalized vice coordinates. So in a way, the data is already on the final coordinates, let's say. So which way is usually the best? True. But this is kind of the thing because it can't be like this explanation because like why would they be doing the conversion inside here if they are passing as normalized device coordinates? That's the thing that it doesn't make sense to me. So I have to spend more time thinking about like what is the correct way to phrase this question so I can clarify the doubts that I have. So I'm gonna be right back. I think I'm gonna go over the 3JS stuff after I'm back. And then I'll spend some time thinking about this, then I'll stop streaming and go back to studying this stuff off stream. I'm gonna be right back. So the thing is that I don't know if the articles, like maybe they explained this, but I didn't pay too much attention. Like, because the matrices themselves, I think they contain the information to translate one coordinate to the other. But they also should contain the values of each thing, the values of the coordinates, I think. So they are matrices that contain the values of the coordinates that once you multiply them, you make the translation from one coordinate system to the other, I think. So what kind of question can I ask to clarify? I think the main question I have is what exactly should be the formats of the data you're passing? Should the points be in normalized device coordinates like always when you're creating the data? Or should they be something else? I'm struggling to think about a question. Maybe I should go. I think I'm gonna read the articles again. I need to read more times while I remember, like while I have this stuff in mind, so I can pay attention to if there is a place that they talk about. So maybe I can just ask ChatGPT and see what it responds to this one. I think I'm gonna do that, then I'm gonna go over the 3JS code. Working with mother graphics APIs like OpenGL or Vulkan, it's common to pass vertex data in normalized device coordinates. In this is a standard coordinate system that ranges from 1 to 1. So I guess the reason why is multiplying by... Obviously, the reason is to get the coordinates of the thing, the data you're passing, in whatever world and camera you're using. So mainly the camera, I think. Yeah, it is the camera. It's actually the world because this is the matrix that represents the object, this one represents the camera, and this one represents the 3D effects that you're gonna have. So yeah, it's just translating the coordinates of the data into the world position by doing these multiplications. And the final thing is gonna be on normalized device coordinates, I think. So the question is if you pass in a different coordinate system, then you probably should convert, like do one extra step. This is the stuff that I'm not really sure. While in local coordinates, vertex data is often initially defined. These local coordinates are transformed into world coordinates through a model matrix. The model matrix includes transformations like translation. So you're doing the multiplication. Yeah, that makes sense. So the projection matrix normalizes the final result. So like you're going from normalized coordinates here. then this one gets the normalized coordinates in relationship to the model place in the visualization. Then you multiply this by the view to get the view of the camera in relationship to that model. So this one is the local. The multiplication is the local place, local coordinates for the data you're passing. Then you're multiplying by the view to get the position based on relative to the camera, and then you multiply by the projection to get the normalized device, the final normalized device coordinates. So you start with normalized device coordinates, which is the A position. Then you go from the local, then from the camera, then normalized coordinates again, but that this time is going to be the final position in road space, but in normalized device coordinates. I think that's what's happening. Typically occur inside of the vertex shader. I think that this makes sense to me now. So the way you do it is just by passing normalized device coordinates. So maybe the other question that I have is, like, because you don't know where the coordinates are gonna be, how can you structure the data? I think that's probably a better question. I guess I guess I understand. It's just because this is gonna be X, Y, and Z, and then obviously it's gonna depend based on how many points you want to draw, and that's gonna be related to all the stuff on the buffers and the indices. So once you break everything down, it's just gonna be points. So it's just gonna be X and Y and Z directions. So like these coordinates are not, it doesn't matter the position that they're gonna have in the final visualization because they are more in relationship to the structure itself. So it's like more, the question is more like it's possible to build the geometry without knowing the location that the geometry is going to be inside of the visualization, because the geometry is just the data of the points. So I think I understand now. That's the part that was kind of confusing to me. So the reason why this is on normalized device coordinates is because it's easier, because the final coordinates are going to be normalized, so you don't have to do another transformation if you're passing in other coordinates. But there is this question about the floats though, the size of the thing. So I guess the the size of the float determines the size of the object. So, but like the question that I have is like, how do you know? I think that on a practical example where you have the data that changes, like which can change with based on events or things like that, then obviously the values are gonna change over time, like each frame depending on what happens on the visualization. Yep. I guess it's possible to know because it's gonna be -1 to 1 regardless at the end. So you don't need to know the overall visualization to know the size because it's always going to be from -1 to 1. So the float, the magnitude of the float just determines the scale of the object, and the place you put the values determines the geometry of the object. And you don't need to think about the whole visualization, the whole scene, in order to create the data because that's just related to the object itself and because you know what's the scale of the final thing is going to be. So that's probably the reason why they use normalized the various coordinates. So because you know it's always going to be from -1 to 1, you have an idea of how the data should look like, the size of the floats here, depending on what the size of the object you want to be on the scene. So I think that makes sense now to me. So now, like what I have to understand is like more complex examples. The, so the thing that and I've seen this in the past on other projects and other things, but probably what happens is that the more complex it becomes, you just create other functions to abstract away all this stuff here. And then you just choose, you're probably going to choose the dynamic one instead of the static for some situations. And then the only thing that is going to change is the data you're passing. So I think that the classes are structured in this way, and I think in 3JS that's how it happens as well, where like you're going to have predefined variables that are going to be related to the way that the data is structured, but then the class receives as arguments, and then it allows you to customize the data based on whatever variable you pass. So I think that's I'm gonna go over this stuff here. So I remember I was thinking about translating stuff from 3JS to C++. I remember that it's more complicated because the way you have to understand how 3JS renders stuff is based on the renderer, which is this main class here, because that's the class that is gonna. I'm not 100% sure if I think it is the class that creates this scene. And then based on the scene, you add objects to the scene, and then each object is going to be a class. And then like this class, which is a mesh, is going to have two different classes, which is another mesh. which is going to be a material and a geometry. So all meshes are created from material and geometry. And a good way to think about it is that geometry is just the vertex shader, and the material is just the fragment shader. So the class is an abstraction that is going to have the variables that are going to determine how the shaders are going to look like, based on like the variables that they set up the shader with. So the shader code has a bunch of variables. The fragment's going to have uniform variables, I think, and other, I think, varying variables. And the vertex shader is going to have variables as well. Then the geometry class is going to be the one that is going to predefine the positions for the structure, the geometry, using the vertex shader. And the material class is going to be the one that determines what kind of color it's going to have and the other properties, like how it's going to react based on light, how much is going to reflect, how much is not going to reflect, those kinds of things. So that defines the material. And then there's another class that is called the mesh, which merges these two classes together. And it's kind of like thinking about creating a program based on the vertex and the fragment shader. So the mesh is the final product and is the class. So that's how the structure of 3GS. Everything inherits from object 3D, which is the template that all the classes use. And then these classes accept information based on the arguments when you're initializing them, and then based on that data, it's gonna create shaders, the shader code. But the thing that is kind of complicated is understanding like what shader is gonna use for each class, and how exactly is rendering the shader. So there's a bunch of abstraction that they create here to make it so that you can have a couple of functions like accept any shader. So like it's a more generic function that accepts anything. And then it allows you to create pretty much any object you want, any class you want, and then pass to these functions here to see what shader is going to be used to draw each thing depending on which class you're using. This is the reason why it's kind of more confusing, because then it becomes like, how do I know exactly what shader each class is using? So I have to remember exactly what I did here, but I went like over like the execution here and then just pretty much assume things and like follow the path. But when you initialize the canvas, and then initialize the context at some point. The WebGL context. It has a bunch of other stuff that is gonna be data related to the visualization. Viewports. So I think it's inside this function here, which is initialize the context, which happens when you call the WebGL renderer in the beginning. And that's all these classes are going to be used to render everything, to like create the graphics pipeline that renders stuff. So obviously based on the names, this one is going to handle the material. This one handles the programs. And the attributes. Attributes are variables inside of the shaders. The attributes and uniforms and varyings, I think. Then you have this one. So I think that this one is used on some of these other ones. So this is related to the buffering of the shaders. Just managing. I want to remember, I think it's on render. But pretty much the files that it uses are this one, the shader chunk and the shader lib inside of these folders here that are inside of the renderer, I think, renderers. So the main class there, the one that I was looking at, this one, is gonna eventually use these two files here. These two files that determine which shader is gonna use from here to draw stuff on the screen. And the code that they use, they assume that they're pretty sure that they use to create the materials that I was using, which is basic material, no, material basic, mesh basic material. This material and the sphere geometry are this shader here, the mesh basic. Obviously, you can like just see based on the name. And then the geometry one. I think that they use only this one, and then this has both the vertex and the fragment shader. So the thing that is complicated here is that you can see that they use a bunch of includes. So I assume that what's happening is that this shader here is gonna use all the like a bunch of other ones to determine what's gonna happen. And I think the reason why they do like that is so that they have more flexibility, because they don't know what you're gonna draw. So they put a bunch of code on the shaders because they become more generic this way, and then it allows you to use anything like, or a bunch of different classes use the same shaders to to draw everything. So I haven't looked into this code yet. Let me go back to I think this is the one that I was looking at. So I think that I'm not 100% sure, but I assume that these are the functions that they work as an interface from the buffer that we're just looking at from OpenGL. But obviously it's the buffer from WebGL, but it's pretty much the same logic. So the classes are from JavaScript, and then they have all the code that is used to create the buffers programmatically that are going to be used by the other classes. So I assume like this is going to be one of the geometry classes, which can be any geometry we want. Like in the case that I was drawing is the sphere geometry, and then materials I think is the basic one, the mesh basic material. So this is how I think it works. And this one is gonna this is gonna contain information about how to pass the variables to the buffer, to use the variables inside of the shaders to draw stuff. So it just has a bunch of variables that are gonna manage the how to draw the stuff you wanna draw, and then all the other geometries are gonna inherit from this one, because this is the base one that has the necessary information to create the shader, or to pass the data to the shader. And then the class itself, this sphere geometry, receives these variables here, and then these variables, I think that what they do is just determine how the data, which is the vertex and the normal, or the vertices, normals in indices, which is the same thing that we're looking at here. So it's pretty much the same thing. So the class there handles everything. And then these, I assume that these are the like predefined calculations of how to structure the data. So you have a circle, and then they allow you to put some arguments here that like give you some flexibility on how the circle is going to look like, which is pretty much determining how many triangles you want to use to create the circle or the sphere. So probably for if I don't use the library here, which pretty much we probably did like something similar, I think that the way to do it is just to copy this code here, because this is probably constructing the data from the points, which in this case would be the vertices here and the indices. that have the values that you should pass through the shader or through the buffer, so that the buffer passes through the shader so that it draws stuff. The thing that is kind of confusing is all the hierarchies and how they relate to each other. This sets the values inside of the shader. I assume the position is probably an attribute inside of the shader codes, which is probably going to be this one or whatever. It's going to depend on the material I think you use, what kind of vertex shader you're going to use. But assume inside of this, one of these includes here, they're going to have probably a variable that is position, another normal, another UV. But maybe not, maybe because this is from probably the buffer geometry. So this is storing the attributes, the variables that the thing is going to use. And the mesh, this is the final one that accepts this one and the geometry. So the material is this one that I was using, which is pretty much the same thing, but for the fragment shader. So these are probably all the variables that the shaders from 3JS use, and then this class just manages the variables on JavaScript, and then based on the rendering pipeline, which is going to be handled by the main class here, it uses both of this class. So yeah, this one handles the fragments, this one handles the geometry, and then both of them are used on this one. That this would be the class that is the abstraction that contains the final program, I think. So this is building the vertex, this is building the fragments, the base classes, and then this is going to be build the final program. And then I think that this one is used on the final, on this other one, the renderer, to actually pass the data to the shaders. And they're using raycast here to render things. Yeah, so this is the conversion there from the article. So it's getting the inverse matrix. So it's going from local coordinates to world coordinates, I think. Probably. And what I assume that the function is doing is just the thing that I talked about, where it's shooting like a light to see if it hits or something or not, and then based on what it hits, it draws the geometry. But I think is this one, probably. Not 100% sure, but I think it's this one. So there's another one that I remember seeing, which is render, I think. Then the render uses that other function to render objects, probably. There are some other functions here that there's some stuff about creating the actual program from the shaders. I think this is the main one that renders stuff on 3JS. So this one probably calls the other one. I think the objects is this sort objects here are the objects that it has to render, the objects that are part of the scene. Because on 3JS you have to add, I think you call scene.add or something like that. So every time you add an object to the scene, it's just going to create that dependency between matrices. So I think that it stores the objects that has to render at each rendering cycle on these objects. And this is the function that renders, I think. Render scene. Depth buffer is a buffer that is used to task to see which objects are in front of each other, I think. But I don't know if I saw the other function. I think the easiest thing to do is just do Control F. 'Cause I don't remember how I got to the other function, the render buffer. Because I think that this is the main one that is related to the shaders, and it's probably this thing here. This is the main function that is responsible for actually getting the shader code to create the visualization. But I don't remember how I got here. So it is on the render object. So just pass the geometry, the material, the objects. And then this one, I think is this one. That is gonna see which shader you're gonna use based on whatever geometry and material passed here to render everything. So I think all that I will have to do if I want to convert this one to the other one is just get the main thing is the data and understanding how the variables are created on each class to structure what's going to be passed to the shaders. But I'm probably going to use the other project though, because they probably have done this already. But if the other one doesn't work, then that's probably what I'm going to do. Just go over each class, then just convert the class to C++, and then I think the main thing is the data, the most annoying thing to figure out. The rest seems like very simple. The data and the coordinates are the most annoying thing. I don't remember now where did I get to, but I remember that there is a maybe it's in the beginning. Yeah, I think it's on the beginning that one function is initialized with a class, and then another. I think it's this class here. I think that this function render buffer uses that class, but it's not with this name. Is with another name. As this buff renderer here. Yeah, here. So this is inside of this function. And I think that this is the one that renders, so it's this class pretty much. This one. And this calls the GL, which is the context from WebGL, which has the function draw arrays, which is the same thing that is happening here pretty much inside of the loop. The GL draw elements or draw arrays. On the other example, I think it has that. So I think it's the same thing that is happening. Yeah, GL draw arrays. But here the GL is going to be the context when you create the canvas, which is created when you initialize this class here, WebGL renderer. And then inside of that buffer renderer thing is going to call this function here. And then the start and the count is just things that are determined based on the classes, the geometry classes you use or the mesh. one of them. Yeah, and then here is the generic function. So based on whatever extension you have, it's just gonna call based on the method name. Is either this one or this one. And then it calls the function based on the parameters here. And I think that this is the one that renders that uses the buffers to call the shaders to do the whole pipeline and then draws the stuff on the screen. Yeah, this starts. No, it's not this one. Maybe it's another. Oh, here, draw range. So yeah, it is from the classes. Depending which geometry you use, it's just gonna pass this stuff here inside of the other function. Inside of this. So I think this is the main entry points, the main point of connection from 3JS to the shaders. And then the structure of all the other classes manage the data that is used to pass through the shader. And then obviously you have the logic. I don't remember exactly where I found this, but it is somewhere. The logic that determines which shader is going to be used based on which class you're using in the beginning to create the geometry and the mesh. But these are the shader code, I think. So yeah, the most difficult part is like understanding how this one works, and then understanding how the classes structure the data to create the geometry and the fragments. So I think I'm gonna stop here. I'm gonna read these articles off stream, and there's a bunch of videos to watch as well. I'm not really sure how long it's gonna take to watch and read all this stuff, but I'm gonna read some of these articles again to clarify these points of confusion. Then I'm gonna probably watch a bunch of videos, and then I think the next thing that I'm gonna do is either study. I think I'm gonna study this thing here, because now it's more clear on my mind how it works. And after I read again, it's probably gonna be even more clear. I think already probably I'm gonna have to study Raylib again to understand on the context of Raylib, how Raylib manages everything. Because the next thing that I want to do is just create shaders based. I want to create the same geometries and materials that 3JS creates, but on C++, and using the Raylib libraries. In Raylib also, they have a struct that is for material and another struct for mesh, but I'm not really sure if it's worth using that. I think it's going to depend on this project here, because I'm going to try to get the code from the classes from this project and then incorporate them on using the Raylib code. Or maybe I'm not really sure if it's better to decouple them and try to decouple as much as possible so that the classes don't rely on Raylib. I think that probably would be better. So maybe I just grab the classes from this one that use straight from OpenGL. Then use those classes to create simple visualizations using Raylib on the other project. Then to create the same visualization that I have, the same structures, the arrow, the edges, and the balls, or the spheres. Once I'm able to create the same materials, also the label is going to take a long time. So I'm going to have to study the fonts and all of this stuff. So once I can create each one of them, like all the geometries and materials that I need, then I'm going to go back to the other one that I'm using Boost to create the graph, and then I'm going to combine both of them to build the graph network with the new shaders, And then once I get to the point, then I'm going to start working on the other project to create the physics simulation. Then after I close the loop, then I probably create another project, and then I'm going to go back to studying Python to create the visualization based on the Python data from the parse tree. So not really sure when I'm going to come back, but this is what I'm going to be doing next. So probably in 1 or 2 days from now or something like that. So